Today we will start with solve some logarithmic equations, then we will look at some word problems. So let's look at the first equation. Log of x plus 2 minus 3 equals 1. The strategy is to isolate the log term by moving everything else to the right hand side. And then we're going to rewrite the logarithmic form into exponential form using the definition. This gives us x plus 2 equals 10 to the power 4. And then we solve for x. Okay. And the solution is 9,998. So don't forget, when we're solving logarithmic equations in general, you need to check whether that solution will make the logarithmic form well defined or not. So we do have a condition which require the argument of the logarithmic form to be positive. And that shouldn't be any problem for this case. So this number is the solution of our logarithmic equation. So next, let's look at the second one. ln of 3 over 8 times x plus 1 equals 10. This equation itself already have the ln term isolated on one side. Okay, so we're going to rewrite this with exponential form as we did previously for log with base 10. So ln, recall that this is logarithmic form with base e. E is the Euler number. So this gives us 3 over 8 times x plus 1 equals e to the power 10. This is a linear equation. We solve for x. This is the exact form of the x value. If you want to approximate this with a decimal, with 2 decimal places, this is what that number is going to be. Again, as a good habit, you want to check whether the number you get will make this logarithmic form well defined by checking whether the argument is going to be positive or not. There is no problem for this case, but in general you want to check that. If you have more complicated expression for the argument, the number you get may violate that condition. Eventually you have to rule out those solutions. Okay, so this is about solving logarithmic equations with one log term, right? Basically, the strategy is to isolate the logarithmic form and then rewrite it into exponential form, then solve for it. Don't forget to check the conditions. Next, let's look at some word problems. Here is a decay model of a certain radioactive material. So the initial amount of this material is 34 grams. And then it's asking how long will it take until 20 grams remain. So in other words, after how many years? We're talking about number of years here. T is in unit years. After how many years the remaining amount of this material is going to be 20 grams. So using this model, so our A of t is going to be 20. And I want to solve for t. Okay, so this gives us an exponential equation. To solve for t, we're going to isolate the exponential form, okay, by dividing the coefficient on both sides. If to simplify it, it's 10 over 17. Next, we're going to take the natural log on both sides. Using the properties of logarithmic form, in this case, is easier to see from definition. So ln of e to the power a for any a is just a. Okay, so by definition, the logarithmic form gives you the exponent, the base needs to be raised to in order to get argument. So that exponent is going to be a. Okay, so that's why this is a property of logarithm form. You can take this as an identity. So with this, so exponential form and logarithm form got cancelled. Really, this brings down the exponent. And the right-hand side is a number. We're going to evaluate this at the very last step. And then we solve for t by dividing the coefficient on both sides. This is the exact value for our t. If you want a decimal approximate for this number, you can use your calculator to calculate it. So calculators have built-in functions for natural log and common log. If you keep 2 decimal places, you're going to have 217.47. After this number of years, the remaining amount of that material is going to be 20 grams. Okay, so now let's look at another example. So use either the compound interest formula or the continuous compounding formula to answer the following questions. Part A, how much should be invested to get $2,000 after 6 years at 6% compounded semi-annually? Okay, we're talking about compounding interest, and it's not continuous compounding. Semi-annually means interest is compounded twice per year. Okay, so we're going to use this formula here. It's asking how much should be invested initially. So P, the initial investment, is unknown here. Total balance after 6 years needs to be 2,000. This 2,000 is our balance, A. 6 years is our T. N is the number of times the interest needs to be compounded per year. In this case, it's 2. And this little r is the annual interest rate in decimal. So 6%, if you convert into decimal, that's 0.06. Okay, so plug these numbers into the compound interest formula. We have this equation. And we're looking for P. This is actually a linear equation. This entire exponential expression is just a coefficient for the unknown P here. Okay, if you simplify this, it's just 1.03 raised to power 12. And you divide by the coefficient on both sides, you have the P value. Again, this is the exact value for our initial investment. If you want a decimal approximate, that's going to be 1,402.76. And you can get this with your calculator. Next one. How long does it take $1,700 to double if it is invested at 5% compounded continuously? Okay, so we're going to use this formula to solve this problem. So the initial deposit is $1,700. The annual interest rate is 5%. We want to solve for the number of years in order for the initial deposit to double. In other words, the A value is going to be twice the amount of P. And R is 5%, 0.05. We're looking for T here. Okay. Again, we'll plug the numbers into this formula. That's going to give us this equation. Double the initial investment equals initial investment times e to the power of the annual interest rate times the amount of time it takes for the initial investment to double. And this gives us an exponential equation because unknown is at the exponent of this exponential form. And then we're going to use the same strategy as we did for the previous word problem to solve for t. We're going to isolate the exponential form by dividing the coefficient on both sides. And then we're going to take the natural log on both sides to get rid of this exponential form. So we know exponential form and exponential function and logarithmic function of the same base are inverse of each other. So this property shouldn't be a surprise to us, right? Eventually, the effect to the exponent from this exponential form and the logarithmic form will be cancelled out. So that's why on the left-hand side, it's just the exponent, 0.05t equals ln2. And then you divide it by the coefficient on both sides. This gives us the exact value for the amount of time it took for the initial investment to double. You can use your calculator to get a decimal approximate for this number. That's going to be approximately 13.86 years. Okay, hope this helps.